Greetings, everyone. My name is Lidian Kivyutomo, and today with my group mates, Kevin Mahardika Mulya and also Evan Varian, will be representing Group 12 from Venus University School of Computer Science. Now, today we will be presenting our research titled Predicting Measles Incidence in Tropical Countries Using Time Series-Based Machine Learning Models.
Before we begin, let us briefly walk you through today's outlines. We will start with the background and introduction, followed by research gap and objective, or hypothesis and methodology, the implementation and dataset, the model we use or result, and finally the discussion and conclusion. Next. Let's start with background of our research. Measles remain one of leading causes of childhood mortality worldwide, despite the availability of effective vaccine for decades. Notably, tropical countries face unique environmental transmission risks that differ significantly from temperate regions. In addition, fluctuating vaccine coverage and unstable herd immunity often trigger periodic outbreak. This continues to be a persistent challenge, especially in regions with developing health infrastructure. Next. So, what exactly is measles? Measles is highly contagious infectious disease caused by measles virus, primarily affecting children under 5 years of age. It will remain one of leading causes of childhood mortality globally, particularly in developing and tropical countries where healthcare infrastructure is still limited. Why is it still a problem today? Despite the existence of effective vaccines, several factors contribute to this fluctuating vaccine coverage across regions. Declining herd immunity in underserved population, unstable and complex transmission cycle driven by climate and human mobility, and inconsistent public health response in low-resource setting. In tropical countries like Indonesia, measles transmission is particularly unpredictable due to unique climate conditions, high population density, and variable healthcare capacity. This is where machine learning has increasingly been explored to support disease prediction and outbreak mitigation strategies. Next. Based on literature review, we identified 5 key research gaps. First, most published studies on measles prediction have been conducted in temperature or high-income countries. While tropical countries face very different environment, demographic, and healthcare challenges. Second, very few students have directly compared ensemble machine learning models such as random forest and gradient boosting with classical statistical models such as ARIMA, specifically for measles prediction in tropical region. Third, many forecasting models rely solely on historical case count without incorporating vaccination coverage metric, namely MCV1 and MCV2, which are critical determinants of measles outbreak risk and population immunity. Fourth, the period from 2020 to 2024 saw significant disruption in health data due to the COVID-19 pandemic. Yet, most exciting studies have not addressed how this data volatility affect model performance. And five, there is no widely accepted standardized evaluation framework that consistently assesses multiple models using the same dataset and metric in the context of tropical measles incident. Next. Based on this gap, our research has 3 main objectives. First, to compare ensemble machine learning model, random forest, and gradient boosting with ARIMA for time series-based measles prediction across tropical countries. Second, to evaluate model performance using 3 metrics, RMSE, MAA, and R2 score. Third, to provide a predictive framework that can support public health decision making. Next, we formulate 5 hypotheses for this study. H1, ensemble machine learning model are expected to outperform classical statistical model. H2, integrating vaccination data is expected to improve prediction accuracy. H3, random forest is expected to achieve the best overall performance. H4, ARIMA is expecting to perform better, especially in low volatility scenarios. And H5, data disruption, particularly from the pandemic period, are expected to limit overall model performance. Next.
Now for the methodology. We adopted an experimental quantitative research design using historical data from the World Health Organization. Our workflow follows a standard machine learning pipeline: data collection, preprocessing, model training, evaluation, and finally comparison and prediction. During preprocessing, we handled missing values, treated outliers, and applied numerical standardization to ensure the data was ready for all 3 models being tested. Next. Now, what we did, First, we used a dataset sourced from the World Health Organization, which includes annual reported measles cases as well as vaccination coverage data for MCV1 and MCV2 across tropical countries. Second, we applied a standard machine learning preprocessing pipeline to ensure the data quality and consistency as shown in the flowchart on this slide. Starting from the data quality checks, outlier handling, implementing the three models, training and validation, evaluation, and ultimately selecting the best model for outbreak prediction. Next. During implementation, the raw WHO dataset went through several important steps. We performed data cleansing to remove duplicate entries and standardize formats across countries and years, handled missing values using strategies that preserve temporal integrity, applied numerical standardization so that feature scales were consistent, particularly important for ensemble models, and manage outliers carefully to avoid distorting training while preserving critical outbreak signals. There are two key implementation decisions worth highlighting. We deliberately did not use mode because this oversampling technique would disregard the temporal order and sequential dependencies inherent in time series measles data. We also avoided linear interpolation. Next. Now for the dataset, our dataset was sourced from the WHO Global Health Observatory, covering reported measles cases by year across tropical countries, spanning several decades. The data sources are listed in this slide. The features we used include country, year, number of reported cases, and vaccination coverage percentage for both MCV1 and MCV2. Next. We used three models in the study. ARIMA as our baseline is a linear time series forecasting model that captures trend and seasonality in sequential data. Random forest, an ensemble method, builds multiple decision trees on bootstrap samples with random feature subsets, then averages the outputs for a more robust prediction. Gradient boosting, also an ensemble method, builds trees sequentially, with each tree correcting the residual errors of the previous one, powerful but sensitive to noise. We selected these three models because ARIMA serves as the traditional statistical baseline commonly used in time series forecasting random forests. Meanwhile, random forest is capable of handling complex, nonlinear, multivariate relationships, while gradient boosting is known for its ability to iteratively reduce prediction errors. Next.
Okay, now we have temporal features, and to enable time series reasoning within the tabular model architecture, three temporal features were engineered per country before training, which are cases lag 1, which is the cases from the previous years, cases lag 2, which is the cases from 2 years prior, and cases rolling 3, which is a 3-year rolling mean of prior case. Now, these lag features will allow the models to learn the autoregressive structure of measles outbreaks, where prior case burden is a strong indicator of future incidents. A label encoded region variable was also included to capture regional epidemiological baseline differences. Now, next on to the results, as we can see here from the table, random forest performed the best out of the three models, which is an R2 score of 0.4541. Gradient boosting comes second with a R2 score of 0.379. As finally, the ARIMA model, which is 0.2629, which is the worst out of the three. The feature importance are in analysis of the random forest feature importance scores reveals that the dominant predictors of prior years reported case count, which is labeled as cases lag 1. Cases lag 1 carries an importance score of 0.871 out of 1.0, and this confirms the strong autoregressive structure of measles incidence that shows that countries with high case burdens in year T-1 tend to sustain elevated transmission in year T. This reflects the multi-year cycles of susceptible population accumulation tied to birth cohorts and vaccination campaign timing, and the 3-year rolling mean, which is the cases rolling 3, and the 2-year lag, which is the cases lag 2, contribute secondary importance scores of 0.034 and 0.032 respectively, providing medium-term trend context. MCV1 vaccination coverage contributes an importance score of 0.028, while MCV2 contributes 0.02 and region encoding contributes 0.015. Now for the discussion conclusion, the discussion is that random forest is the best out of all three models, which is the highest R2 score of 0.45541. And ARIMA is the weakest performer with the lowest R2 score of 0.2629. And gradient boosting is the middle ground, and the second one, which is the R2 score of 0.3790. And R2 score is limited by data volatility. Overall, R2 score is around 0.4 due to high instability from from the year 2020 to 2024 because of the COVID-19 pandemic effects. Now, conclusion and future work would be random forests outperform ARIMA and gradient boosting for measles predictions in tropical countries, and future work. So that means that For future works, explore deep learning architectures LSTM for long-term temporal dependencies, integrate additional environmental and demographic datasets, as well as build real-time prediction systems for public health decision-making. That is all from our group. Thank you for listening, and goodbye.